I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today, we discuss the variational principle. Variational principle from classical mechanics. Second topic of classical mechanics is variational principle of MSc first and semester first. Before that, in last topic, Lagrangian formulations of classical mechanics, we study the tools of tools in the hands of mathematicians, only the coordinates, and before using this coordinate, generalized coordinate, a mathematician describe the motion of a particle and also path followed by them. The particle can be discussed in Lagrangian formulations. Therefore, information of the path y is equal to f of x, whether the function is minimum or maximum at a point, can be obtained from differential calculus by putting first derivative of y constant, y dot is equal to 0, and the function is either maximum or minimum. By second derivatives, by the test the value of the second derivative of the function at that point. If the second derivative is negative, then we say that the function is maximum at a point, or if the second derivative is minimum, if the second derivative is positive, then the value of the function, we decide the value of the function is minimum at that point. However, if we want to know the information about the whole path, we use integral calculus, the technique of the calculus of variations, and are called variational principle. In this topic, we study the complete path of the whole path of the functions, and with the use of calculus of variation, and this principle is known as variational principle. The calculus of variation has its origin in the generalization of the elementary theory of maxima and minima of functions of several variable or more variable or single variable, etc. The history of calculus of variation can be traced back to the year of 1696, when John Bernoulli advanced the problem of the point Bartosztochrome. In this problem, one has to find the uh, curve connecting two given points A and B that do lie on a vertical line, such that a particle studying down this curve under gravity from A reaches point B in the shortest time. Apart from the problem of Bartosztochrome, there are three other problems exerted great influence on the development of the subject, and these are the problem of geodesic, the problem of minimum surface of revolution, and the problem of isoperimetric. Thus, in calculus of variation, we consider the motion of a particle or system of particle between 2 points along a curve y is equal to f of x, that is 2 points p of x1 y1 and q of x2 y2. Then distance from p to q is denoted by ds, and is equal to square root of distance formula, change in coordinate dx, x coordinate change in dx, and y coordinate change dy, denoted as, therefore ds is equal to square root of dx square plus dy square. Hence the total distance between 2 points P and Q along the curve is given by I y of x is equal to integral from x1 to x2 1 plus y dash square raised to 1/2 square root of 1 plus y dash square dx, where y dash is equal to dy by dx. And in general, the integrand is a function of the independent variable x and the dependent variable y, and its derivative is y dash. Thus, the most general form of the integral is given by I of y of x is equal to integral from x1 to x2 f of x y dash dx. This integral may represent the total path between two given points, the surface area of revolutions of a curve, the time for quickest distance, depending upon the situation of the problem. The functional I in general depends upon the starting point x1 y1 and end points x2 y2, and the curve between 2 points. The question is what function y of x, so that the functional y of x has stationary value. Thus, in this topic, we study the first, the condition of the satisfied by y of x, such that the functional I of y of x define f of y of x is equal to integral from x1 to x2 f of x y f of x y y dash must have extremum value. Therefore, before that, studying in this topic, the before with the use of variational principle, uh, we study in the Newtonian equations, Newton's equation of motion, Lagrange's equation of motion, Hamilton's equation of motion, Schrodinger's equation of motion, Einstein field equation of gravitation, and Hoyle-Narlik's equation for gravitations, and so on so forth, by slightly modifying the integral. Here basic lemma, some introductory part. If x1 and x2 greater than x1 are fixed constant, and g of x is a particular continuous function for x1 less equal x less equal x2, and if integral from x1 to x2 g of x eta of x dx is equal to 0 for every choice of continuous differentiable function eta of x, such that eta of x1 is equal to 0 is equal to eta of x2, then g of x is equal to 0 identically in x1 less equal x less equal x2. Then prove that eta g of x is equal to 0. Suppose that lemma is not true. Let us assume that there is a particular value x dash in x of x other than x in the interval such that g of x dash is not equal to 0. Contrary, suppose that assume the g of x dash is greater than 0. In between x1 to x2 there are point x1 dash, x2 dash. Since g of x is a continuous function in x1 and x2, and in particular it is continuous at x is equal to x dash, hence there must exist in interval surrounding x dash may x1 dash less equal x less equal x2 dash, in which g of x greater than 0 everywhere. Let us now see whether the integral from x1 to x2 g of x eta of x dx is equal to 0 for all permissible value of eta of x. We choose eta of x such that eta of x is equal to 0 for x1 less equal x less equal x1 dash, and is equal to x minus x1 dash square bracket square into x minus x2 dash bracket square for x1 dash less equal x less equal x2 dash is equal to 0 for x1 dash less equal x less equal x2. For this choice of eta of x, which also satisfies that eta of x1 dash is equal to eta of x2 dash is equal to 0. The integral from x1 to x2 g of x eta of x dx becomes x1 to x2 g of x eta of x dx is equal to integral from x1 to x2 g of x eta of x dx plus integral from x1 dash to x2 dash g of x eta of x dx plus integral from x2 dash to x2 g of x eta of x dx, and this is equal to variational distance formula, integral from x1 dash to x2 dash x minus x1 dash square bracket square into x minus x2 dash bracket square g of x dx. Therefore, since g of x greater than 0 in x1 dash less equal x less equal x2 dash, therefore RHS of equation is definitely positive, that is integral from x1 to x2 g of x eta of x dx is greater than 0, which is contradictions to our hypothesis. Therefore, integral from x1 to x2 g of x eta of x dx is equal to 0 if g of x dash less than 0, and we obtain the similar contradiction. This is contradiction arises because of our assumption g of x not equal to 0 for x1 to x2. This implies that g of x is equal to 0 identically, and hence complete the proof. Theorem first. Find the Euler's differential equation satisfied by twice differentiable function y of x, which extremizes the functional I of y of x is equal to x1 to x2 f of x y by dash dx, and hence we solve.